All right, so yesterday we started out talking about naming simple covalent compounds that contain only two different types of elements. And we said whenever you do this, you have to use prefixes, right? So the mono, di, tri, tetra, and so on. The main things you have to be aware of is you don't use mono if it comes first, and you use tetra instead of quad. So just pay attention to that. And then in addition, you need that IDE suffix. So these are pretty straightforward, simple to follow. Today we're going to look at ionic compounds. Oops. And we're going to try to figure out how to name ionic compounds. And there's actually two different naming conventions for ionic compounds. So I'm going to break these up into two groups. So two types of ionic naming. All right. The first one is with a group 1A or 2A cation. So where's group 1A or 2A? Far left-hand side of the periodic table, right? It's those first two columns. So if you have a cation in those first two columns, you're going to follow that naming system. And then second one is with a transition metal. And if you remember, the transition metals are smack in the middle of the periodic table. They're that lowered set of rows between group 3B and 2B. All right, so let's take a look at the group 1A or 2A naming. And this one's easier. All right, and with group 1A or 2A naming, there's a simple naming convention. And the naming convention goes like this. You first list your cation, just like we did. I think we did a few examples where I said try to have your cation first. And then you follow it with your anion with an IDE suffix. Does that make sense? All right. The main thing to note is you don't use prefixes. All you do is have your cation, your anion, and then an IDE suffix. So let's take a look at a few examples. And I'm going to do some practice. Let's do the ionic compound that forms between potassium and oxygen. And what I want us to do is write out the molecular formula, and I'll just abbreviate that MF, and then we'll do the name on the other side. So let's do a little bit of practice with that. So if you remember with the molecular formula, the easy trick you can do is to draw out your cation and your anion, right? So potassium would be our cation. What charge does potassium always have? 1, right? So it'd be 1 plus, since it's a cation. And then we've got oxygen over here. What charge does oxygen have when it's ionic? 2 minus. Okay, and then really easily what you can do is flip these around. We saw that yesterday. And that means that this must be K2O1. Do we have to include the 1? No, you don't have to include the 1. It's implied if you don't have it drawn there. So this would just be K2O for the molecular formula. What would the name be now? Potassium goes first. And then it would go oxide. The IDE suffix is there. Students will often ask, well, why don't we do the mono, di, tri, tetra? Wouldn't that make it easier? In this case, it's assumed that potassium oxide is always going to be K2O in order to have your charges balance. So they just say it's assumed, it's implied, you don't need mono, di, tri, tetra for these simple ionic compounds. Does that make sense? Let's do a few more. And this time I'm just going to give you the molecular formula, and I want you to find the name. So I'll do molecular formula over here, and the name over here. Let's do Ca3N2, and then for the second one, I'm just going to give you the name, and I want you to find the molecular formula. We'll do calcium sulfide. So then the question is, what's the name for this one, and what's the molecular formula for that one? So I'll give you guys a minute to work on this, and then check with your neighbor and see if you agree. See a show of thumbs. Who thinks they got it? A few people? Want to start with the easy one? We'll go from the molecular formula to the name. So what would the name be for Ca3N2? Be calcium. That's the cation. It goes first. We don't need to say tricalcium. It's implied. All right, and then what goes next? Nitride. So you don't need to say dinitride, it's implied there. All right, now the trickier one is calcium sulfide. If we think about this, calcium, the elemental symbol is Ca. What charge will it always have as an ion? 2+, okay. And then sulfide, sulfur will have what charge? 2-. All right, so if we take this, do that flip method that we did before, some students will write out Ca2S2. Would that be the most appropriate? No, it's not the least common denominator. So what I would do is just try to simplify it. A 2-to-2 ratio is the same as 1-to-1. So let's just keep it as CAS. Does that make sense? So I do want you guys to be able to go back and forth between molecular formula and name. It takes a little bit of practice, and I think on Monday I'm just going to spend the whole period doing naming activity. But I do want you to practice as much as possible over the weekend. Yeah. Oops. Oh, in the name or the formula? So because they're canceling out, you don't need to show any net charge. You only show a charge if there's an overall negative or an overall positive. If they cancel out, you don't need to show anything. Good question. All right. So I'm just going to erase this to get more space in here. The next one we have to do is transition metal naming. All right, and this was the group 2 naming that we talked about, and this also has a special naming convention. And just like before, your cation goes first. And then next you have a Roman numeral. How many of you remember Roman numerals? I know it's not super well taught anymore. It's kind of an old school naming convention, but we'll do the easiest ones. And then after that, you have a space. And then just like before, you put your anion, whoops, with an IDE suffix. So if you remember, 1 as a Roman numeral is I. 2 looks like that. 3 looks like that. 4 is where it gets tricky. 4 is IV, like that. 5 goes out to just V, and then 6 goes to VI, like that. So I'm not really going to go above 6. You won't see those very often, but these are kind of the bare basic Roman numerals you should probably remember for your science courses. They may show up in other classes as well. Does that make sense? So let's do a few practice ones. We'll do FeCl3. So first thing we want to do is we want to name our cation, which in this case must be iron, right? The problem with iron as a transition metal is if you look at it on the periodic table, it's right smack in the middle. It doesn't have a predictable charge. Iron can be all sorts of different charges. And so what we need to do is we need to indicate what charge iron has. So I'm just going to put a question mark here for that Roman numeral spot, because we don't know whether or not it's +1, +2, +3, or so on. But we can infer it. And the easiest way to infer it is from the chlorines, right? So let's say we have an iron atom with some sort of charge. We know it's going to be a positive charge, but we have 3 chlorines. What charge must chlorine have? -1. It's in group 7A. So I'd say 1 negative, 1 negative, 1 negative. All right, assuming that our charges cancel, what charge must the iron have? Must be +3 to cancel out the 3 negatives, right? So all I'm going to do is say this must be 3+. So when we go ahead and we do our naming system, I say iron 3, and then we want our anion, which is chlorine, but with an IDE suffix. Does that make sense? So when you are stuck, use your anion as a guide. The anion charge will help you predict what the charge must be for your transition metal. So we'll do a few more practice ones, and I'll show you why this matters. Let's do CuBr. And for our second one, I'm going to do CuBr2. I know this is super fun. I remember being really frustrated as a student where I was like, why do we need to name all this stuff? And my professor at the time had one of my favorite answers. He said, it's so we don't point and grunt at things when we're trying to describe them. All right, let's try this as a class. So for example, copper is a transition metal. We don't know what charge it has, but we know we have 1 bromine. And what charge does bromine have? 1 negative. Okay, that means that the copper must be what? Yeah, so it must be +1. Okay, that means that when we name it, it must be copper 1 bromide. All right, down here it's pretty similar. Again, we don't know the charge on copper. It's a transition metal. It goes all over the place. But now we've got 2 bromines, each with a 1 negative. It doesn't matter if you do 1 negative, in my opinion, or -1. Some teachers are picky. All right, what charge must this have now? +2. Okay, so when we go ahead and we name this one, it would be copper 2 bromide. That's why I get really nitpicky, is I hear students occasionally say copper bromide, and I'll say, which one? There's actually 2 very distinct types. One is a brilliant, brilliant blue color. That copper 2 bromide is this gorgeous blue. It looks like a tropical ocean. Copper bromide, the top one, is reactive with air, and it's kind of this dull gray powder. So they're radically different compounds due to the different types of copper in there. Does that make sense? All right, so pay attention. Anytime you see any element from that center block, the transition metal block, you should immediately think, I need a Roman numeral. All right, now we've got to switch gears to one of the trickier parts of naming, and this has to do with something called a polyatomic ion. Yep?
If there's no number in it, do we assume it's a 1? Or do we assume that they're just not giving it to us?
If you see a transition metal and there's no Roman numeral, it's just unclear. You don't know which one they're talking about, as long as you're looking at the name. If you're looking at the formula, you can infer the charge of the cation. Yep. All right, so polyatomic ions are a little tricky, but I'm going to try to narrow down the ones we need to know. And these are charged species containing more than one atom that is covalently bonded to another atom. And it's a little bit confusing, but I'll show you a few examples. So in this example, I've got sodium, and then I've got OH. What charge does sodium always have? It's in group 1, so it's got to be 1 plus, right? So we know sodium is 1 plus. And then over here, we've got this OH group. It's not another atom, so we can't determine the charge of it. However, we can treat this as an entire unit. So it's actually 2 atoms making up the anion. And what charge do you think it must have? -1. And so what students will often do is they'll show that in brackets, and they'll say that must be 1 negative in order to counteract that sodium. All right, and let's take a look at kind of what's going on here with the Lewis dot structure. And I'm going to try to make it simple. Sodium, as a neutral element, has how many valence electrons? It's got to have 1. Okay, and then OH, as a neutral species, we know oxygen has 6 valence electrons. We know hydrogen has 1. So what we're going to do is we're going to try to pair up the O and the H because they are covalently bonded together. So I'm just going to show this as a bond like that. But if you notice, sodium's not happy because it has an unpaired electron, and oxygen's not happy because it also has an unpaired electron on the bottom. So what essentially happens is there can be a transfer of electrons from the sodium atom over to the OH group. So when this happens, the sodium, because it lost one of its electrons, must be positively charged. It's going to be 1 plus. And then the oxygen over here, because it stole an electron, this oxygen must be 1 negative. So if we look at this entire unit here, this is an anion because it has an overall -1 charge. But it contains a covalent bond within it. Does that make sense? It's a little bit strange, but there's only a handful of them that I want you to know. I'm going to actually go ahead and delete this table because it's a little bit overwhelming. And I'm just going to draw out the ones I want you to remember. And these aren't very easy to memorize, I'll be honest with you, but what I did up here is I've got a Quizlet link. How many of you have ever used Quizlet? It's pretty handy. So what I really like doing is playing with this on my phone, even just between classes or on the bus or wherever. And after you do it a certain number of times, it just gets drilled into your head. But more repetition is key. So try to use Quizlet or flashcards. And I'll show you how to do some of these games here in a second. All right, so going back to this, polyatomic ions to memorize. I'm going to make a list where we've got charge over here, the name over here, and then the formula on the right-hand side. All right, the first ones we're going to look at are going to be +1 charge species. And there's one that's called the ammonium ion. And the ammonium ion's formula is NH4, and it has a positive charge of +1, so we're just going to show a plus next to it like that. So that's one of them you should know. It's common in biology, that's why I want you to remember it. The next one we're going to do is -1. This is hydrogen carbonate. However, chemists will often call this bicarbonate. They mean the exact same thing. And this is HCO3, and it has a negative charge overall. And then after that, we've got another one that's -1, and this is acetate. And the acetate ion can be represented a few different ways. So CH3CO2 minus, or you can represent it as C2H3O2 minus. You might see it written both ways, so I do like to show it both ways. I kind of prefer the CH3CO2 minus because it lets you know a little bit about the connectivity of atoms, versus the C2H3O2 doesn't tell you very much about the connectivity. All right, so that's a common one. Next one of my favorite ones, nitrate. The nitrate anion is NO3 minus. That's another common one, so it's a -1 overall charge. Nitrates are really common in fertilizers. When I was in graduate school, we accidentally made a sensor that was really good at detecting nitrates, and before we knew it, my friend had started a company based on our research where we were sticking stakes into the ground and trying to pick up how much fertilizer was being dumped into these fields. All right, next one is a more morbid example. This is a cyanide anion. Tends to be very, very toxic. If you ever watch movies about spies, they sometimes have pills where they bite down on them and it causes them to die almost immediately. Quite poisonous. And this is CN minus. The next one we have that's -1 is hydroxide. This one's very common. In fact, we just saw it in the previous example. This is OH minus, because that oxygen stole an electron from another neighboring atom. And then we're going to go into -2s. For -2, we've got carbonate. And this is CO3 2 minus. Pretty common. It's found in a lot of geological formations. So limestone and things like that have carbonate in there. Next one that's -2 is sulfate. This is often found a lot in geology. This is SO4 2 minus. And the charge should always be superscript. The number of atoms should always be subscript. And then the last one, -3, is phosphate. This is important in agriculture. It's an essential plant ion that they need, and it's also important in human biology as well. And this is PO4, 3-. So I know there's a lot of these. Like I said, this weekend I want you to try to practice using the Quizlet, or just make your own flashcards. You should remember the charge, the name, and the formula. So I'll show you my favorite part of the Quizlet app. It's the matching game. And you can do this for time and see if you can beat your own time. But for example, you could say, oh, there's a Cn- in the top right-hand corner. That's cyanide. I'm going to drop that there. Ammonium ion, I'm going to drop that there. Sulfate ion is right here. Phosphate ion is right there. Hydroxide ion is right here. That means chlorate's left over, and I'm going to pair that up. So I'm only third place right now. But you can do this as just kind of a personal quiz. I'm not going to be super picky with spelling, but I do want it to be somewhat legible. So if I can figure out what you're trying to say, I'll give you credit. But if I'm like, I have no idea what they're talking about, you're going to miss points on it. All right, does that make sense? So let's take a look at a few examples. Let's do NH4Cl. And I'll give you a trick. If you see more than one atom, it is likely polyatomic. At least in this class, we're not going to get into the more complicated examples. So for example, in this one, we've got nitrogen, hydrogen, and chlorine. That means there's got to be some combination of atoms forming a polyatomic ion, right? So if we look at this really quickly, I could say, well, we've seen chlorine quite a bit. Chlorine, we know, is always -1, right? So immediately I could say, this is Cl1-. That means this leftover chunk must have a 1+ charge, right? Does anybody remember the name of the NH4? Ammonium, right? So this is ammonium. And that's our cation. Over here, we've got chlorine with the negative charge, so we want the "ide" suffix. So this would be chloride. Luckily with these, you don't have to worry about Roman numerals at all. So this is just ammonium chloride. Does that make sense? Roman numerals are only ever used if you have one of those transition metals. I will show you another trick for predicting the charge too if you're ever absolutely stuck. And let's do NH4. And let's say theoretically I'm absolutely stuck on what that charge is going to be. First thing I do is I draw the Lewis structure. And then I add or remove electrons. So that all electrons are paired. So let's take a look at the ammonium ion example. We know it's nitrogen with 4 hydrogens. So I'm going to go ahead and say nitrogen, stagger my hydrogens around like this. We know hydrogen always has a valence of 1, so I'm going to put that around it like that. Just going to slide that down. And then the hydrogen on the right also has 1 valence. How many valence electrons for nitrogen? Got to have 5. So I go 1, 2, 3, 4, 5. And then we can start pairing our unpaired electrons. So So for example, I'd say this has got to be paired, this has got to be paired, this has got to be paired, and that's got to be paired. But I got a problem here. I've got this unpaired electron. Would it make sense to add a second electron there or take it out? And why? What would happen if we added one more electron to it? We'd have too many. It'd be more than an octet. We said atoms, if possible, prefer to have an octet, right? So in this example, we could remove an electron. In order to ensure that the nitrogen only has paired electrons around it. And when you do this, you can redraw your ion with all the bonding pairs. The nitrogen lost one electron. So this nitrogen must have a positive charge on it. So if you're ever stuck, you can always default back to the Lewis structures, draw it out, and say, oh, it has to have a positive one charge because that's the only way the Lewis structure makes sense. Does that make sense? All right, let's do a little bit of a flow chart. I like just making a simple flow chart for studying. And the first thing I always ask is my compound ionic or covalent? Whoop. And how can we determine whether or not an ion's ionic or covalent? Who remembers? Yeah, typically covalent compounds are only nonmetals, right? They're only nonmetals, and you can't have any of those polyatomic ions. So let's kind of make a chart here. So covalent compounds can contain two nonmetals. Ionic are different. Ionic compounds contain a metal, a transition metal, or a polyatomic ion. Does that make sense? And if you remember, the trick with polyatomic ions is if you have more than two atoms, there's likely going to be a polyatomic ion there. Okay, and then with covalent compounds, the naming system is pretty straightforward. And the naming system, if you remember, always goes first atom, and then second atom, with an IDE suffix. And the important thing to remember is you may need a prefix. That's the number one takeaway with covalent compounds, is you got to have prefixes there, right? All right. Ionic compounds are a little bit more complicated because we've got the different types of naming. So the first one is with a group, or actually I'm just going to say non-transition metal. And then the second one is if you have a transition metal. All right, and if you remember, the naming for a transition or a non-transition metal is pretty simple. It always goes cation, space, anion, with an IDE suffix, versus the naming for a transition metal. What was different? Yeah, we had to have a Roman numeral. And I'm just going to abbreviate the Roman numeral as the number that corresponds to it. And then we go anion with an IDE suffix. Does that make sense? So quite often, students will get mixed up with which naming convention to use. That's why I want you to practice it a lot. And when we come back on Monday, we're just going to do a ton of practice. So if this is confusing, don't be alarmed. We're hopefully going to work through enough practice problems where it helps.